I have opened the device studio that is called a graphical user interface for NanoDCAL. So I will try to build the structure in this device studio. First of all, I click on build option and click on Graphene Nanoribbon. The new window has opened where I can define the type of element that I want to make the design here. I can define the bond length of my passivations of dangling bond. I can activate this checkbox and define the chiral vector as per your requirement. Let's suppose I take default one and click on preview button. I can visualize my structure nanoriver in this preview option, and then I can click on build button to build in my dashboard, and I can see in any of the view. I can rotate it simply and any format visualization x, y, or y, z, zx, whatever plane you want to visualize, it can be visualized. Now I want to repeat the structure in transport direction, that is called C direction. So I will go to the builder and click on redefine crystal. I want to define this crystal repetition 15 times in C direction. So I will change it to repetition in C direction and click on preview button. Now 15 times it is repeated in C direction, then click on build button. Now my nanoribbon sheet has been prepared with the passivation of dangling bond. Hydrogen atom is there on top and bottom side, which is showing in the white color, and all middle region are carbon atom. Now I want to make the device structure, so I will click on this convert to device option. I can select the left and right electrode and click on right electrode and click on preview options. I can increase the thickness of left and right electrode. By default thickness has been created. I can click on build button to build this device structure. In this project var, there are 3 input file has generated. The first one that I has created as a nanoribbon, then I redefined 15 times in C direction, and then I made the device. So 3 file has created. Now I would like to simulate these devices with including the Spintronics feature. So I will click on simulator and NanoDCAL and click on FCF calculations, where I will define the density functional theory DFT calculation parameter. By default electron temperature energy cutoff. Now I will click on simulator and click on NanoDCAL and go to the FCF calculations, where by default electron temperature energy cutoff exchange correlation functions are defined, and k point sampling number by default is given. These are all default parameter. Contour integral, electrode biasing. At without biasing it will simulate. First we can apply some voltage on left and right electrode later on. First of all we want to simulate this device at equilibrium conditions, so there is no biasing we want to apply initially. And then iteration control parameter, which will solve the Hamiltonian equations first, and basis sets are there. We can upload our own parameter. User defined basis set is also supported. We can add the doping in the semiconductor layers. Now I want to include the effect of spin parameters. So I go to this spin type and select the collinear spins. Spin orbit interaction is also possible in this NanoDCAL software. I want to click on generate file. Once I click on generate file, there are 3 folders has got generated. That is called device, left electrode and right electrode. So you can see in this device region there is one left electrode is there, right electrode is there, and central scattering device region is there, that we can rotate this device structures. Now I want to add my analysis parameter as an input. So I go to the simulator and NanoDCAL and go to this analysis option. Now here I can add the electrode analysis part. So I will select either device parameter or electrode material parameters. So this NanoDCAL software can calculate the material parameter as well as the device parameters. So for this device there are 3 parts are divided. One is called left electrode, second one is called right electrode, and device. I have selected this left electrode, where I can select my analysis. These are all analysis which is supported in this NanoDCAL device studio software. I want to select few of them. Suppose you want to calculate the band structure. I double click on it. It is added in my selected options. Similarly, I want to calculate the total electron density. So I will click on this add button, and then I want to add the effective potential. So I can click on this effective potential. Similarly, if you want to calculate the eigenstate, I can click on eigenstate, or you can add the complex band structure, you can add the charges, whatever you want to plot, and you can add the potentials and different kind of potential like effective potential, Hartree potential, action correlation potential. So you can choose from here. Suppose from all of these analysis part, I have selected 7 analysis. So these I want to calculate. So I will click on generate file. Now for left electrode, all my analysis input file has generated. That you can see here. There is one SCF electrode input file. All are analysis input file. Similarly, I will generate the file for device analysis. So I go to the simulator NanoDCAL and go to the analysis one. These are my device property. Suppose you want to calculate the density of state for device region, and you want to calculate the transmission coefficient. So I will add it here. And you want to calculate the total electron density, or you want to calculate the effective potentials, or you want to calculate the Seebeck coefficients, conductance, or you want to calculate the IV curve and thermoelectric currents and potentials. So these are all options you can calculate by using this device regions. So now I want to generate the file for device 1. Now my device property analysis input file has been added in my device folder. Now I want to simulate the file which is there inside each folder. So I want to simulate first of all this left electrode material. So I will right click on this SCF file and click on run button. And here I can also run the calculation parallelly. So whatever number of cores in your system, you can run the calculations on your cluster workstation. Now suppose as an example, I want to run 8 core calculation on my 8 core machine. I will click on run button. Now in the bottom bar, that is called job manager, the calculation has started to running the program. Now you can see the status of the calculation is running. So in the meantime, I can put my all calculation in the running conditions. So I want to put in the queue. I have run the queue, this my band structure one. You can see it is in the queue category. So that automatically it will start the program. Once left electrode SCF input file have finished the calculation, band structure.input file will execute the program. Similarly, I will click on electron density.input file and I will click on run button. I have to run all my analysis input file in the running conditions. So I want to put a queue, so that automatically the program will get started. Once top one will finish the calculation, then next one will start the program automatically. That's why I am putting this in the run the program. Now you can see in top my program is running. All my analysis input file are in queue. Once the calculation of top electrode is finished, we can visualize this electrode material output. Whatever analysis we have selected, all these output we can plot it. So it will take some time. The time simulation dependent on the machine, how much your system configuration is, and how many atoms are there in your device structures. So dependent on the device structure, your licensing configurations as well as your system configurations. Since left and right electrode is having similar material, so I want to write to simulate only SCF input file of my right electrode. So I click on it and run the program. So left and right electrode has started the calculations, and once the calculation of left and right electrode finished, then this output of left and right electrode will be called in this SCF input file of the device one. So that will automatically load in the device region. The left and right electrode output will be loaded in the device scf.input file. So parallelly I want to run the calculation for my device regions, so that I will visualize my all output simultaneously once the calculation finished. Now I click on run button and click on the run program. The calculation is running the program. Whatever it is going to finish in the job manager, it is showing the finished program and running program and queue program. I want to run my all device analysis input file. To run it, so I will select one by one and click on run button. Now it is running. Once the calculation finished for all this analysis input file and the device one, then we can visualize our output in the device studio, as well as it is also integrated with the MATLAB software. So results can also be visualized in MATLAB as well as in this device studio. You can also export your raw data in standard text format or image format. The raw data can be exported. So I have run the program. So calculation is running. We have reached this till complex band structure calculations. Then next charge calculation will start the program, and one by one these all will start the program. Once the calculation for finished, then we can visualize the output. Even we can also see the output parallelly. Suppose left electrode, few of the calculation has finished. So if you want to see the output of band structure and other property, let's say example left electrode top SCF input file that has finished the calculations. Band structure has finished the calculations. So we can also visualize the band structure calculations. You can see it is already generated. I can click on right click and click on show view. This is a band structure of left electrode. It is at spin up condition. If you want to see at spin down, you can see there is spin up, spin down, or spin up and spin down both at a time. This is a spin down calculation of band structure. And if you want to plot both, you can click on both spin up and spin down. It is now plotting. You can see the output. Red graph is showing for the spin down and blue one is called for spin up. If you want to export the image, this raw data, you can click simply on the export button, and there is an option called you can save your file in the form of PNG, JPG, PDF, TIFF format, text format. You can select the particular format, and wherever you want to save your file, you can simply click on save button. Your data will be exported in text format or image format. Similarly, all plot like total electron density plot has generated. I can right click on show view, and you can see that only left electrode is initially started the calculations. And this is a 3D view of total electron density for left electrode. And if you want to see the 2D view of this left electrode electron density, this is a left electrode electron density in 2D plot in x direction, along y direction, along z directions. So x, y, z in all direction, you can plot your output, and you can also zoom the particular regions. And you can see the Bundy plot as well. So 1D, 2D, 3D, all are possible. In any plane, you can visualize the output. And there is next one is called eigenstate, that is also calculated. So we are seeing the output, whatever it is has finished the calculation, that output can be plotted and we can visualize it. It is eigenstate 3D view and band value for spin up, spin down. And this is 2D model in along x-axis, along y-axis, z-axis, and Bundy plot. And some other calculation is running. So once the calculation for all other analysis input file finish the calculation, then we can also visualize our output. So it may take some time. I will show you the calculation results once the calculation for all this program has executed. Now the simulation has been finished. You can see all the input file has finished the calculations. So I would like to show you the device output. I will go to this folder, and left electrode output I already showed you. Left and right electrode is having similar material, and I would like to show you the device output. So if you want to see the density of state, you can right click and click on show view. Now you can see this is a density of state from minus 11 electron volt to plus 11 electron volt, the range that is specified here. You can change the range as well, and then click on apply. So from minus 10 to plus 10, spin up density of state calculations. If you want to see on spin down, you can select from spin down. This red one graph is showing the spin down calculations. And if you want to see both at a time, you can select both spin up and spin down density of state calculations. You can export this graph as well. You can click on export and save in the form of image, JPG, BMP, PDF, TIFF, EPS, Excel, or text format. You can save the data and click on save on desktop. It can be saved. Now similarly, I can visualize some of my other output as well. That is called transmission coefficient. Right click and click show view. This is transmission coefficient for spin up calculation, and this is for spin down calculation. It is both spin up and spin down calculation transmission coefficient from minus 10 to plus 10, and this is total transmission coefficient. Both are there. Now similarly, if you want to see a total electron density, right click and click on show view. This is total electron density plot. It is a 3D view. In the central region, you can view any plane. 3D viewer is there, XY, YZ, ZX, whatever the plane you want to see the visualization, all options are there. 3-dimensional plot, similarly 2-dimensional plot for total electron density. You can zoom also particular region. You can draw the rectangle, it can zoom it as well. And along x-axis, y-axis, or z-axis. And similarly 1-dimensional plot for total electron density. In any plane you can visualize. If you want to see the Seebeck coefficient, right click and click on show view. This is Seebeck coefficient for spin up and spin down on multiple temperature. You can see the chemical potential on different energy and temperature. It is plotting the output. And if you want to see the chemical potential, this is like chemical potential, energy, and on different temperature multiple graphs are plotting. If you want to visualize the Seebeck coefficient on particular one value, you can select that particular value, like here 250 is selected. So this is spin up and spin down Seebeck coefficient at 250 Kelvin temperature. And similarly Seebeck spin and charge coefficient. This is Seebeck spin and charge coefficient plot, and with respect to chemical potential and with respect to temperature. So whatever plot you want to visualize, it can be done in all this similar manner. And similarly, if you want to see this thermoelectric current exchange correlation potential, like I click on the exchange correlation potential. This is exchange correlation potential, 3D view, 2D view, and 1D view. And if you want to see the current versus voltage graph and thermoelectric current, then you have to take the help from MATLAB. It will generate the file for MATLAB. So I would like to open the MATLAB. These plot can also be integrated with MATLAB as well. So you can extract the data in MATLAB. So Device Studio is open visualization tool, as well as extraction option is there. Now MATLAB is open. I would like to load the directory of my project. So I click on this browse button and go to the desktop, and this Graphene Nanoribbon and this device one folder that I want to load in my MATLAB current voltage value. Then you can load this current voltage curve.mat file, that is MATLAB file. I have loaded the file. Then type data. It will show that voltage equal to 1 and that's why the current equal to 1. Voltage at contact number 2 equal to 0 and current equal to 0. Since I have not applied any biasing, that's why current on electrode 1 and electrode 2 both are 0. If I will apply the biasing, then the current will be changed. Like thermoelectric current, I can click on it and load this file, drag and drop and type data. It will show the thermoelectric current. 1 minute, I can type right now. Now it is plotting at electrode number 1 thermoelectric current value and electrode